Now let us see heat conduction through a composite wall. A composite wall is a wall made up of more than one slab. So here we have one slab identified as 1, and we have another slab which is identified as 2, and we have another slab which is identified as 3. So the slab 1 has a thickness of L1, and its thermal conductivity is K1. Slab 2 has a thickness L2 and its thermal conductivity is K2. Slab 3 has a thickness of L3 and its thermal conductivity is K3. So this kind of arrangement we call it as a composite wall. For example, the walls which are made up of bricks. So if you take that as an example, on the inside of the wall we have a thin paint layer. After the paint we have the plaster. After the plaster we have the actual brick, and after the brick on the outside we will have a layer of plaster, and after that we will have a paint layer. So there are 5 layers in an actual wall. So that is also an example for composite wall. If you take the example of your bench, so the bench or the desk, at the top there will be a lamina, and below that there will be plywood. Plywood is also a composite wall. It is made up of different layers, and at the bottom there can be paint or there can be another lamina sheet. So that is another example for composite wall. So wherever we have two solid surfaces which are in contact with each other and heat transfer is taking place through conduction, then we can call them as composite wall. And we encounter composite wall in our engineering problems almost every time. So now let us see how the heat transfer occurs in a composite wall. And the composite wall can be arranged in two different manners. One is here you have one layer after the other. The same arrangement can be rotated by 90 degree. Then you will have one layer above the other. So heat will be flowing from left to right or from right to left, but the layers will be one above the other. So that arrangement we call it as parallel arrangement, and this arrangement we call it as series arrangement, because heat is flowing through each of these slabs one after the other. Again, the assumptions which we made in the previous case, that is one-dimensional steady-state conduction through a slab. So the same assumptions holds good here. We assume one-dimensional conduction through all the slabs, and we assume the surfaces are isothermal, that is the temperature at the interface remains constant. Then we assume the thermal conductivity remains constant. Then we assume there is no internal heat generation. So if you observe this diagram, on the left side the heat is being added to the composite wall with the help of a fluid. The fluid is flowing and it has a temperature TA and it has a heat transfer coefficient HA. So here the main assumption is that the temperature of the fluid on the left side is greater than the temperature of the fluid on the right side. Right side also we have a fluid and that's temperature is TB. So we are assuming TA is greater than TB, and because of that the heat is flowing in the positive X direction, that is from left to right. So on the right extreme side we have another fluid. So here the fluid is a temperature TB and it has a heat transfer coefficient of HB. So on either side we have convective boundary condition for this problem. Now let us see, or let us estimate the heat transfer rate through each layer. So that is, first we have convection here, then we have conduction through slab 1, conduction through slab 2, then conduction through slab 3, and then we have convection on the right surface of slab 3. So you can see that here heat is flowing in this direction. So heat flows through each material one after the other. So the amount of heat flowing through each slab as well as convective heat transfer will remain same. So Q remains same for all the cases. So first case is convection at left end of the composite wall. So here the heat transfer is given by, we know that the convective heat transfer is given by HA into area which is surface area of the slab multiplied by TA minus T1. Or I can write, so this can be written as, I need TA minus T1, so that will be equal to Q divided by HA into A. So the temperature difference TA minus T1 will be equal to Q divided by H into A. Now I'll consider conduction through slab 1. So here the heat transfer Q will be equal to K into A divided by K1 into A divided by L1. Area remains same for all the materials, into T1 minus T2. So this is the equation which we derived in the previous session. So K1A divided by L1 into T1 minus T2 gives us the conduction through this slab. So here also I need temperature difference. So I can write T1 minus T2 will be equal to Q divided by, I'll write it as L1 divided by K1A. Sorry. I'll write it as Q into L1 divided by K1 into A. Then we have the third one, that is conduction through slab 2. Here also the heat transfer rate remains same, that is Q will be equal to K2 into A divided by L2 into T2 minus T1, because for slab 2 T2 is the temperature here and T3 is the temperature here, so it is T2 minus T3. So T3 is the temperature on the right face of the slab 2. So from this I can write T2 minus T3 will be equal to Q into L2 divided by K2 into A. Now I'll consider the fourth case, that is conduction through slab 3. So here on the left face the temperature is T3, on the right face the temperature is T4. So Q will be equal to K3 into A divided by L3 multiplied by T3 minus T4. So this can be written as T3 minus T4 will be equal to QL3 divided by K3 into A. And the last one is fifth one, that is the convection which is occurring on the right face of the slab 3. So convection at right end I'll write it here. Q will be equal to, for convection it is HB into A into T4 minus TB, or I can write T4 minus TB will be equal to Q divided by HB into A. So now we have TA minus TB, we have TA minus T1 as Q by H into HA into A, T1 minus T2 as Q into L1 divided by K1 into A, T2 minus T3 as L2 divided by K2 into A, T3 minus T4 as L3 divided by K3 into A, and T4 minus TB as HB into A. Now what I'll do is I'll add all these equations. So I'll add, you can call it as equation A, this is equation B, this is equation C, this is equation D, and you can call this as equation E. Now what I'm going to do is I'm going to add equation A, B, C, D and E. When I add that, on the left hand side I have TA minus T1 plus T1. So minus T1 and plus T1 will get cancelled. I have minus T2 and plus T2 here, that will get cancelled. I have minus T3 and plus T3 here, that will get cancelled. I have minus T4 plus T4, that will get cancelled. So on the left hand side I'll be left with TA minus TB. On the right hand side I'll add all the terms. So I'll go to the next page. So here on the left hand side we are left with TA minus TB, that will be equal to, the first is convection, that is Q divided by HA into A, plus then we have conduction through slab 1, that was, for that it was L1 divided by K1 into A, plus for second slab it was L2 divided by K2 into A, plus for third slab it was L3 divided by K3, this is small k, K3 into A, plus for convection it was Q divided by HB into A. Now Q is common in all the terms, although area is common I will not take it out. So I'll write Q into 1 divided by HA into A plus L1 divided by K1 into A plus L2 divided by K2 into A plus L3 divided by K3 into A plus 1 divided by HB into A. If you remember the previous classes, we had talked about thermal resistance, and for conduction it was 1 divided by H into A. For convection it was 1 divided by H into A. For convection it was L by Ka. So here we have the resistance for convection. Since it is we are using abbreviation A here, I'll write it as RA, plus we have R conduction through the first slab, that is I'll call it as R1, plus resistance for the conduction through slab 2, R2, plus resistance for conduction through slab 3, that is R3, plus resistance for convective heat transfer on the right face, that is RB. Or I can write Q into summation of thermal resistance. Now I rearrange the term, I need Q, so Q can be written as, this is TA minus TB. So Q can be written as TA minus TB divided by summation of thermal resistance which are involved in the process. So if we don't have convection over here, if we don't have convection here, then we will not consider that. If we don't have convection here, then we will not consider that. So whatever the things which are present here, that needs to be added, and that is what this circuit shows. So in this circuit we have 1, 2, 3, 4 and 5 resistance. So these 5 resistance are happening because of convection, then conduction through slab 1, conduction through slab 2, conduction through slab 3 and conduction through slab 4. So here the interface temperature, so here the temperature is TA, then at the surface we have temperature T1, then the interface between slab 1 and 2 we have temperature T2, then the interface between slab 2 and 3 we have T3, then at the end of the slab 3 we have T4, and the fluid at the end we have TB. So the heat is flowing throughout all the slabs, and the heat flowing is same or constant. So this is the equation for heat transfer, that is heat conduction or heat transfer through a composite wall.